Welcome, ladies and gentlemen, to our second chapter of our second year course in structural geology, fresh from Rhodes University. This chapter deals essentially with the Moore stress diagram and its applications. It is split up into three separate parts and also three separate video clips. The first part deals with fracture types and different types of stress and stress nomenclature. If you are sufficiently familiar with that, you might want to skip this section and go straight for the second and the third part, which introduce the Moore stress diagram, explain what you can do with it and how it works, and how we can use it to assess the likelihood of reactivation of faults and what the influence of fluid pressure changes in the stability of rocks. Fractures that most geologists will know from almost any outcrop with consolidated lithified rocks are joints. Joints are tensile fractures, mode 1 fractures. They are usually present in various sets in different orientations, and they indicate that across the fracture loss of cohesion has taken place. Mineral bonds, atomic bonds have broken across these planar, usually planar, sometimes irregularly shaped surfaces. There is normally no significant dilation. These are just cracks, and what we do not find along joints is displacement along the fracture surface. Shear fractures and faults are different. The displacement along the fault surface can be very small, but it also can be very large, over several orders of magnitude. But along shear fractures and faults, we do not find significant dilation. And dilation means an opening up of space between the two fracture surfaces of the two neighboring blocks of rock. Then there are hydraulic fractures. Hydraulic fractures are important because along of such fractures, veins usually can form, hydrothermal veins which may or may not be mineralized, and they play a very important role in the reconstruction of the history of rocks and regions, and they are particularly important for the formation of mineral deposits. These hydraulic fractures can also be mode 1 fractures. They can show significant dilation. Some hydrothermal veins are tens of meters thick, and their formation is driven by the fluid pressure exerted from hydrothermal fluids. A second type of hydraulic fractures forms similar structures, but in these kinds of transitional tensile fractures or faults, we find a combination of tensile opening, creating the space for the hydrothermal vein that goes together with lateral displacement along the fracture surface. These two fracture types, they have their equivalent, of course, in the brittle field without the presence of hydrothermal veins. Transitional tensile fractures and mode 1 fractures have been discussed in the first part of this lecture series. Here we see some examples what jointing can do. We see here on the left image the upper part of the Ograbi's waterfall in the northern Cape of South Africa. Quite a spectacular waterfall in the rainy season, and we see here in the background granitic gneisses that have mode 1 joints, sets of mode 1 joints. Some of them are subhorizontal. These are the faces facing upwards. Towards us is a second joint set developed, and we see here steep joints, fairly narrowly spaced here in the central part. These joints are laterally quite extensive, and they are pointing straight along the gorge that the Orange River forms here. And there's good reason to believe that the loss of cohesion along these joint sets formed blocks that are relatively small and could be easily eroded by flooding events, by high water levels in the Orange River, such as we see here in the rainy season. That has formed this very impressive gorge of the Orange River just downstream of the Ogravis Falls. Here we see an example for a fault. Clearly there is a very sharp tectonic contact. If we assume that this is a dip-slip fault, it would be a reverse fault with the hanging wall block moving upwards and the footwall block moving downwards. Here on the right hand side we see the situation in Eastern Anatolia, where large-scale fault systems form structures of plate tectonic significance. The North Anatolian dextral fault zone here in the north, and the East Anatolian fault zone, several others here including the Central Anatolian fault zone. Of course, if we want to understand how such large-scale plate tectonic processes work, we need to understand how fractures and faults formed in the first place. Here we see hydrothermal veins. We see two types of hydrothermal veins. Mode 1 tensile fractures formed these veins that we see here on the left hand side. The opening direction is indicated by the arrows, and if you investigate a little bit closer, you will see fibrous quartz crystals growing in this direction, perpendicular to the fracture surfaces that form the boundary of these veins. These vein orientations indicate the direction in which the vein has opened, because the crystals form more or less simultaneously from the fluid that is present when the vein opens. That would be a mode 1, simple mode 1 tensile fracture. On the right hand side we see oblique fiber orientation. We see here quartz fibers that are not perpendicular to the fractures of the veins, and this indicates that this is a transitional tensile fracture that opened with a tensile component creating the space and some lateral displacement, top to the left, bottom to the right in this case. So the fiber orientation is one of the first things you would want to investigate when you look at hydrothermal veins. If you are lucky, it is very straightforward to distinguish mode 1 joints from transitional tensile joints, and you can draw your conclusions on the modus of fracture formation when fluid was present and the structure formed. Stress in general is a force that is acting on a given area. So the very basic definition is F over A, defined as a vector acting at a certain magnitude in a certain direction onto an area of a given size. Any stress vector acting at a certain magnitude in a certain direction can be split up into a normal component, the normal stress acting perpendicular to the surface under consideration, and the shear stress that acts parallel to that surface. We will see in the more stress diagram that these two stresses, normal stress and the shear stress, and their absolute and relative magnitude to each other, are decisive for fractures either to form or not to form, or to remain stable or to be reactivated. So shear stresses and normal stresses are very important mechanical parameters, and it is important that we are aware of the meaning of these terms. I refer back to a first year level course on structure and tectonics, on structural geology and tectonics. In chapter 4 we have discussed the difference of stress and strain, and if you feel you might want to revise these, I refer you back to chapter 4 of the first lecture series. Terms relating to stress and sign conventions are important for the Mohr stress diagram. Compressive stresses are expressed usually in megapascals, and they are given a positive sign. This is not a positive sign in the mathematical sense. This is convention, because tensile stresses are expressed also in megapascals, but they are given a negative sign. So if we are talking about stresses that pull outwards, we would give these stresses a negative sign. everything that pushes material together is a compressive stress with a positive sign. Let's make an example about lithostatic stress. Lithostatic stress at depth obviously will increase because with increasing depth, the overburden of rocks that act at a specific point in the interior of the Earth will increase. Let's have a look at an example of a granitic terrain and let's look at a surface area at the bottom of a 1 cubic kilometer of rock material, granite in this case. We want to find out what kind of stress acts at a depth of 1 kilometer. So what we need to consider is the overburden, and that would be 1 cubic kilometer of granite. We can easily calculate how many cubic meters that would be. That would be 1,000 times 1,000 times 1,000 meters. 10 to the power of 9, 1 billion cubic meter. That is what 1 cubic kilometer of granite would be, and the force that would act on an area in 1 kilometer depth would be the 1,000 times 1,000 times 1,000 meters of rock times the density of the rock. Each of these 1 billion of cubic meters would weigh about 2.7 tons, so 2,700 kilograms, times the gravitational constant, 9.81 meter per second squared. This would give us in newtons the force that is acting on a 1 square kilometer surface in 1 kilometer depth, and 2.65 times 10 to the power of 13 newtons is quite a lot. The area onto which this force acts are 1 million square meter, 1,000 by 1,000 square meters. And if we put these two equations into our formula, we see that the area cancels out against 1,000 by 1,000 meters of our granite cube, which tells us that if we just discuss stress at depth, the area itself does not really matter, despite of the definition of stress, which includes the area. The area cancels out through the force that is generated by the volume of rock that generates the force itself. So in order to determine stresses at depth, we have a shortcut. We have a very simple equation: the depth times the density times the gravitational constant, which gives us the stress in pascals. And you see these are fairly large numbers. That is why we use megapascals. In 1 kilometer depth in a normal granitic terrain, you can expect stresses acting of about 26.5 megapascals. We see here this shortcut that allows us to determine the stress acting at a certain depth. The stress is simply the depth in meters times the density of the rock, which you would average, presuming that you have a reasonable knowledge of the terrain, times the gravitational constant, 9.81. That gives you the pressure, and you would express the pressure typically in megapascals. But for tectonic purposes, we need to be careful. This only gives us the lithostatic stress, assuming that there are no horizontal or vertical variations in the stress field. So the calculation that we just have done assumes hydrostatic stress conditions. All stresses are equal. That is what lithostatic pressure usually means, and that is what petrologists usually use in their thermodynamic calculations. This would mean that the stress ellipsoid at the bottom of our granite cube is in fact spherical. Now the point is, for structural geology, we cannot really operate with hydrostatic stresses, because if we have no hydrostatic stresses, we do not have differential stresses, which is the difference between the largest and smallest stress vector. What we require in order to achieve deformation are sufficiently large differential stresses, and that means non-hydrostatic stress fields, such as the stress field illustrated by the stress ellipsoid here on the right hand side. Clearly, sigma 1 is larger than the other stress vectors, which appear to be approximately of the same magnitude. So non-spherical stress ellipsoids, that is what is required to cause deformation in rocks. What we see here is a diagram that illustrates a very early deformation experiment that was done more than 100 years ago. We see here a large block of wax that was put between two wooden planks, and these wooden planks were vertically loaded in order to simulate normal faulting. And what we see here in the result of that experiment is indeed a normal fault has formed, but there are also conjugated fractures that we see here, and a large number of smaller fractures are indicated here and highlighted on that old photograph. When we look at the diagram here on the left hand side, we see the most important players in the generation of such structures. We see here a vertical stress vector, which in the case of this experiment was the largest stress vector and therefore was sigma 1. The horizontal stress was the smallest stress vector, sigma 3. And these two stresses caused a normal fault to form, a displacement along this surface, and we can assume a shear stress acting parallel to the surface and normal stress acting perpendicular to that surface. Then there is this important angle theta that we also will recognize again in the Moore stress diagram. This is an important angle because it describes the angle between the maximum principal stress vector sigma 1 and the fracture surface. This angle theta is very important for the understanding of the Moore stress diagram and for the understanding of rock mechanics in general. The intermediate stress would be sigma 2, and the sigma 2 principal stress vector is perpendicular to both sigma 1 and sigma 3. That means here in our example, sigma 2 would be straight here in the viewing direction, perpendicular to the slide we are looking at. A reminder, the differential stress, of course, is sigma 1 minus sigma 3. This is the main background that you will need to understand the Moore stress diagram, and thank you very much for watching. The Moore stress diagram itself is explained in the following video, the second part of our second chapter in this course. Thank you very much.